Welcome to Bite Size Chemistry with your chemistry cowboy, Dr. Andrew Evans. Today we're going to talk about equilibrium, what it is, how we can find it, and how we can use it. Equilibrium is a state in which the forward and the reverse reactions of a reversible reaction have achieved a balance in the speeds, where the forward reaction and the reverse reaction are happening at a constant rate. At this point, it is like the reaction is on a treadmill. It is moving forward, but it's staying in place. This equilibrium is established only at certain concentrations of products and reactants. This equilibrium is independent of the actual speed of the reaction and is only dependent on the concentrations. This is due to the fact that as the reactant is consumed, the rate of the forward reaction will decrease, and as the product is produced, the rate of the reverse reaction will increase to the point which both the forward and the reverse reactions, the change in molarity with respect to change in time, will reach a middle point. So this does not mean that the amount of products and reactants are equal, only that the rate of change of the products and reactants are equal. If the rate of the forward reaction equals the rate of the reverse reaction, we can set the two kinetic experiments to be equal. At that point, we could solve for the rate constant of each one together, isolating them from the concentrations of product and reactant. These rate constants can then be converted into the equilibrium constant K, capital K, different from the lowercase k's in kinetics. This capital K is a state function. Mind you, unlike kinetics, it does not matter the mechanism we take, only the starting and ending products. Equilibrium does not mean all reactant is consumed or all potential products have been formed. Equilibrium just means that the rate of the forward reaction and the rate of the reverse reaction are the same. The reaction is essentially stopped. This word essentially will be important later on when we understand such things as Le Chatelier's principle. For now, we only need to consider the concentrations of products and reactants at equilibrium. So, as we set up equilibrium for a given reaction, A and B go to C and D, the K expression is always going to be given as the products over reactants raised to the power of their coefficients. I'd like to talk about how to solve a K expression. There are several things you could be solving for in a K expression, but one of the main ones you'll be solving for is the actual equilibrium constant itself. To do this, we need to know the concentrations of all materials involved, at least all materials that are aqueous or gas phase. So I have a reaction right here of N2O4 going to two NO2s. So the first thing I must do is to write the K expression, which is always products over reactants. So raised to the power of their coefficients, because we need to take into account the total number of molecules involved here. There is our K expression. So what do we need to solve? Well, what if in the situation at equilibrium, the concentrations of all involved molecules are 0.5 and 0.325 molars, what will we do? So we've written our K expression, we have our relative concentrations, we will plug them in and evaluate. Now you may note as we do this that K is a unitless expression. If you want to know why, you can go ask me later or ask your local physical chemist, and they'll be glad to tell you why in depth. But for all you people who just want to learn general chemistry, forget about it. It's just one last thing you have to know. Always unitless, no matter what. You plug this in, you solve, and you'll get the K, in this situation, 0.211. Now, what else can we do with K from that situation? Well, if we know K, we can solve for various product or reactant concentrations, given we know the K, of course, and the other components. So what do we do if N2O4 is 1 molar at equilibrium? What would the concentration of NO2 be? Well, if we know that, we can plug that in. 0.211 equals x squared over 1. I've set my product as an x, which I can solve for now. So I multiply the 1 to both sides to get to x squared is equal to 0.211 times 1. And so to evaluate the x, we must square root both sides. The concentration of NO2 is equal to 0.459 molar. Now, what if instead of 1 molar, we're given that the concentration of NO2 the concentration of N2O4 is 0.34 molar. Do that just as easily. Instead of 1 is now 0.34. Once again, we have to isolate the x. X squared equals 0.211 times 0.34, and we'll have to square root, and we'll get that the concentration of NO2 is now equal to 0.268. So, what do you notice? Well, 1 molar gave us 0.459. Well, 0.34 molar gave us 0.268. Less concentration means less to go around. It's going to always change.